because this is the way we want our computers to be. We want them to be reliable, we want them to be scalable, and we want them to be scalable fast. If a decade ago we were willing to wait days for a hardware upgrade, these days we want it to happen in minutes. And so what the cloud provider actually sells is this illusion of an endless amount of computing resources waiting for us to consume. It's like a big bank of computing resources. And like every bank, the biggest fear is of that day that all the customers are going to come and ask for their money. So fraud storms are essentially the same thing. What you can see here is the distribution of the number of subscriptions that are using a certain number of cores. This is in a certain data center in Azure. And you can see that most subscriptions require a small number of cores, and there is a long tail. And if I run this movie, I try to run it here. Again. Oh, sorry. So you can see the progress on the top. I hope you can see it because it's here on the numbers. No, I don't think you... Okay, just a minute again. Let's try again, and if it doesn't work, It's running on my computer, but it doesn't run here. Okay. Anyway, I'll give you the end of the movie. What you can see is that most subscriptions require a small number of cores, and actually this distribution is relatively stable in time. But at this data center, at some point in time, we start to see a sharp rise in the number of cores that are requested for a large number of cores. And the problem with these subscriptions is that they are all fraudsters. I will show you another static slide in the end, so it might help for you to understand. But we get a very large peak here. And all these subscriptions are not planning to pay for the resources they consume. This is a huge amount of resources. Now, in order to support this endless resources illusion, Microsoft has to keep large buffers of computing resources. This is one thing. And the second thing is to detect these fraud storms as fast as possible. So, let's see. Somehow this is stuck. Let's try again. Okay, so to get a subscription in Azure, there are various offer types. You can start with a free trial, which would give you a limited amount of resources, then use a pay-as-you-go offer type, where you pay periodically for the actual resources that you consumed, all kind of specific agreements. And in order to prevent fraud, there are very standard fraud prevention measures, so a capture challenge, SMS challenge, validation of the credit card, and so on. But we cannot have too many of those because in the end of the day, they pose a burden on the regular user, on the legitimate user. And therefore, we also have fraud detection. Now, fraud detection happens at two levels. One is the subscription level. All subscriptions are scanned to identify if they are fraudsters. And secondly, at the data center level. So these are the fraud storms, to be able to identify extreme cases. Now, I hope you all understood, despite the fact that the movie didn't work, what a fraud storm is, and now I'm going to go into the technical part of the talk. So I'm going to start by describing the problem formulation. We'll compare a supervised approach with an unsupervised approach, present some real-world challenges that we encountered, and some snapshots of the system. So the data that we have is a two-dimensional time series containing the hourly number of new subscriptions and hourly number of cores that were used in every data center and every offer group, offer type independently. We analyze them independently in order to gain maximum sensitivity. And we also have labels. Now, labels for fraud are related to money, and therefore the confidence is very high. They are very reliable. The problem is that we receive them at about an order of magnitude of a month after the payment, because they are coming from the bill of the credit card company not being paid. So, but looking at historical data, we have these labels very reliably, and so we can plot this graph, where on the x-axis you have the time, on the y-axis you have the number of cores that were occupied by fraudsters. So, and the different colors are just different data centers and offer types. And you can see that in many cases it's low, and in some cases start to rise. And we had someone labeling for us the beginning of the fraud storm, the first bulk shutdown of the fraud storm. You would have seen this in the movie, but once a fraud storm is detected, it is once the condition that we currently have a fraudster is detected, it's relatively easy to identify all the related fraudsters because they manage to go into the cloud through the same breach. So they are all together being shut down. And this is the first point in time where the fraudstorm has been detected. But there is still a bug to solve in order for this fraudstorm to disappear completely, and this is marked as the end of the fraudstorm. And so our system is going to run hourly and alert whether we are in a fraudstorm condition or not. And then we would like to measure its performance by three measures: true positive, false positive, and the time to detect, because the sooner we detect it, the more money we save on these excessive buffers. So we have labels, but of course this is a relatively scarce event. And so we have labels, but not too many. So we can choose between a supervised approach and an unsupervised approach. Typically, if we have labels, a supervised approach would work better. But again, we have only few labels. An unsupervised approach, we take an anomaly detection approach. And this might have a relatively high false positive rate because the cloud is a very dynamic environment, and yes, every fraudstorm is an anomaly, but not every anomaly is a fraudstorm. So we have to try both approaches. The first approach we tried with a supervised approach. It has three layers. The first layer is feature extraction. We look at a historical window of the two time series that we have, and we extract past values and all kinds of functions on these features. Second layer is the way we had the continuous label that I presented, the number of cores that were occupied by fraudsters. And then, following exactly the labeling step that we had, we just use a binary classifier to try to know when to alert. Is this a fraudster or not? So we tried to run this approach, and sadly, we didn't manage to identify any fraudstorm, and we wanted to analyze and try to understand which layer is failing. So our first trial was to insert the true values of the second layer into the third layer and see if we can make the prediction. Now, these graphs are a little bit complicated, but they're going to repeat again in this talk, so this is the time. What you see in both plots on the x-axis is the false positive, is the number of data centers and offer types that we're analyzing that had a negligible false positive rate. So it's proportional to 1 over the false positive rate. So 1 would be the best value, meaning no sample set that we analyzed had a false positive, significant false positive rate. On the left, you can see the true positive rate, and on the right, you can see the time to detection. So actually, what you see here are very good results. You can see that there are almost no regions with significant false positive rate. You can see that we detect almost all fraudsters depending on the threshold, and you can see that the time to detection is very good. So the failure doesn't come from the third layer. So it can come from the second layer or from some interaction between them. So we plotted the root mean square error of for each offer group and each region. we plotted the root mean square error of the prediction of the second layer comparing to the true value, and we can see a very big difference between different overviews. So green is very good value and red is very high value. And when we looked at this matrix, it actually reminded us of the matrix of where we had a fraud storm. So these matrices, I think by the eye you can see that it's already correlated, but if you want the number, it's a correlation coefficient of 0.5 with a p-value of 10 to the minus 4. And the bottom line of this correlation is that yes, we can predict the number of fraudulent cores unless we have a fraud storm, which is exactly what we're looking for, so it's kind of problematic, and this sends us to use the anomaly detection model. So the anomaly detection model, again, has 3 layers. The first layer is the feature extraction, and it's completely identical to the previous model, the supervised model. The second layer, now what we're predicting is the value of each of the signals in our time series in the next hour. So what in the third layer, we try to decide, we look at the actual value, we look at the predicted value, and we try to decide whether these two values are different enough, or is this just an expected error? Because of course these are continuous values that we can get the exact value. And we do this using assuming a multivariate normal distribution on the error, and then we extract from this. So what you can see here is the performance of this algorithm, and this is compared to a state-of-the-art algorithm by Twitter that was designed to detect anomalies in the cloud. The basic difference between our algorithm and their algorithm is that our algorithm is multivariate. It operates on the 2 signals at the same time, and this algorithm is univariate. And so in order to combine the results of this algorithm on our data, we run it independently on each of the signals, and then combine the results with different thresholds and with different with an AND or an OR, meaning this is a fraud storm. In one case, if both signals detected an anomaly, and in the other case, if any of the signals detected an anomaly. So in red, you just see the previous the classification results, and our algorithm is here in blue. What you can see is that at the same vertical line, meaning at the same false positive rate, our algorithm reaches a better true positive rate here on the left, and a lower time to detect it. So it outperforms the statement. Now here you can see a visualization of what we're actually doing. In the top 2 panels, you can see the 2 signals that we're analyzing. The true signals are in green, and our predicted values are in black. The purple here on the background is the label that we had. So this is the fraud storm. It was manually labeled as a fraud storm. And actually, if you look here in the bottom panel, you can see this is the continuous signal, the continuous label, sorry. The number of cores that were occupied by fraudsters. And you can see the peak here, which means that this was a fraud storm. And on the third from the top panel, this is our detection. So this is the minus log of the p-value, and the higher the bar, this means we are more confident of the detection, and red are above our threshold. So you can see that we detected this fraud storm that was labeled to us, and you can see that we have some false positive, and in many cases these false positives are related to real anomalies in the signal, as we expected. Specifically, if we look carefully here into this anomaly, which is also anomaly in both signals, we can see here in the continuous signal that there is actually a bump here in the number of frauds. So this is actually, in our eyes, an error in the labeling of the fraud story. There was a weak fraud story. So all this was very nice, and all the data that you saw until now, because this was historical data. The problem with real-time data is that it looks more like this. And it has places where it's corrupted and possibly missing. And of course, we cannot predict anything during the period that the data is wrong, but we would like to recover as fast as possible from this period and go back to be able to predict. So the question was how to handle missing and corrupted data. This is we just made a test. We removed a week of samples before, of measurements before a certain date, and then we evaluate the performance. So this is the performance when the data is fully observed. And now we try to see what happens when we simply ignore these features. And this is the results that we get. So the performance is significantly worse. The true positive rate is smaller, and the time to detect is much higher. And then we try to do a linear interpolation. And actually, we didn't expect it to work that well. But you can see the green line is the result of the linear interpolation over the missing week, and you can see that it almost recovers the yellow line, which is the fully observed. So this is where we stop. Really, it's good enough for us. Second issue is the time to detect. The data accumulation period, the size of the data accumulation period. I mean, in order to, there are two things that comprise the data accumulation period. One is the length of the shift that we take back in order to extract the features. So if we're taking 2 weeks of features, we need at least 2 weeks for this data center and offer type to operate until we can predict. And on top of this, we also have to wait for training data to accumulate. So we wanted to see how we can minimize this data accumulation period in order to be able to operate as fast as possible. So what you can see here on the x-axis is the different, I start with the feature shift that we take, different values, and on the left you can see the true positive rate, and on the right you can see the 1/, false positive rate. And we can see that already after 48 hours, if I remember, I cannot see the numbers here, it already go back to a good true positive rate, and if we continue to add more features, then in 10 days, already the noise, every dot here is a different threshold, and the lines connecting them are the same feature shift. So we see that in the end, even the noise is, when we try different thresholds, is even smaller. The false positive rate is pretty stable all the time. So a feature shift of 10 days should be sufficient. And then, what's the minimal training history? So again, on the x-axis is the period of training history length. And here it's the true positive, here it's the 1/, false negative. And actually, it seems that already with a very small training set, we are able to predict. But if we look here, we can see that the 1/, false positive rate is very low, which means that actually we are alerting every hour, and therefore we manage to predict very well, but we have many, many false positives. After we increase the training history, the performance on the true positive seems to go down, but the false positive improves. And after about 2 months, we reach good performance both in aspects of true positive and in aspects of false positive. So this is how the system looks like. As I explained, it cannot operate from day one, and therefore it runs in parallel to a rule-based system. This is one reason, actually. All the time it runs in parallel to the rule-based, just as a safe measure. But what you can see here is this is a Power BI interface. You can select every region and every offer group, and you can see the continuous plot of the p-value and the specific alerts that rise above the threshold. Now, this is the graph actually that the static graph of what you would have seen in the movie. This is the distribution, the typical distribution, where we see most of the subscriptions requiring a small number of cores. And here you can see the peak during a fraud storm where fraudsters are broken and are asking for a large number of cores. Now, what we learned in this research, and I think it's one of the advantages of the system, is that we can try to model this distribution in many ways. Because if you can see that, at least in this case, all the fraudsters requested exactly the same number of cores. And we could model this. The problem is that we would be modeling the breach, and we would model what the fraudsters are actually after. And by modeling what the fraudsters are looking for, we believe that the system would have a longer life expectancy rather than modeling the breach, because if we close the door, they would come through the window. But if what they are looking for is a large number of cores, this is just what they are looking for, and they cannot do anything else so that it wouldn't show up in our data. Just to summarize, I presented the machine learning approach, compared the supervised approach, and showed that actually in this case the unsupervised approach performs better. Another advantage of this of our system, the way it is designed, is that it is very flexible for addition of new features. So both the second stage of predicting each of the signals and the third stage of multivariate normal distribution assumption on the error. So they are all multivariate, and such systems have to evolve in order to be adapted to the changing reality and to new false positives. So new features can be added once the system is already operating, and it doesn't require any significant change in the algorithm. So this work was a joint work together with Yuda Finkelstein, Amit Ilbuch, Shai Nahum, Daniel Alon, and Elad Yom Tov, all for Microsoft. And thank you very much for surviving.